Thank you all for coming. It's a great pleasure to introduce you Abe Ittycheriah from IBM. Abe got his PhD from Rutgers in 2001, and since he has been working at IBM for many years now, even before getting your PhD, right? So he has been a research staff member in the Natural Language System Group at the IBM Watson Research Lab. Over the last 4 years, his primary focus has been on machine translation and word alignment between Arabic and English. And I should say, of course, that his work has been instrumental in the GALE project for the IBM effort. He is also responsible for the statistical machine translation engine, which is used in several government projects, such as GALE. And prior to this assignment at IBM, he has worked on question answering and telephone speech recognition algorithms and interfaces. Thank you.
Okay, thank you, Damian. So thank you all for inviting me, and I will make some, I'm going to talk about translation today, and I'll try to explain as best as I can. But do stop me at any time and ask questions, and if there's something that's not clear, I don't mind, explaining. So today I'm going to talk about direct models, and this is not a new thing that I invented. It's been around for a very long time, and I think most of conditional models are direct models in some sense. So maybe, we've applied this to translation and gotten some good results. So we call our system the direct model 2, and so we've been using this term. Okay, so let me just set the stage. So we're going to talk about some source sequence. This is some sentence, and it'll be, the symbols S for source, and some target sequence, T. And what we're interested in doing is, for the alignment problem, we're given these sequences, and we wish to find the correspondence between the source and target languages. That's alignment. And in translation, we'll be given just a source sequence. We want to find the T sequence that's optimal under some criteria, and I'll go into that. Oh, okay, so statistical MT, I think many people reference the work at IBM. So by Brown et al. In 1992. This was well before my time there, and I grew up learning this paper. So essentially, you have some conditional distribution. Given some source sequence, we want to produce some T that's the optimal under this conditional distribution. Okay, so they defined this fundamental equation of machine translation. They essentially used the source channel model. They flipped the translation model into being probability of source given target instead of what we're doing, probability of target given source directly. So we will be operating on the left side of this, and they basically did most of their work by doing this type of thing. There's no harm in doing this. In their paper, they say that most of the reason for doing this type of flip is they're concerned about producing things that are observable. And I'll show you how we restrict ourselves to alignments, and really, so we don't really worry about producing target strings that are not well conditioned. P of T is the normal language model. That I'm not going to talk much about today. And most of the work I'm going to talk about is the translation model. Okay, so when I started in this field, I had lots of complaints. And so here's complaint number 1. If you think about translation, you have some writer, and he's grown up with some style, some mood, some spelling, and he eventually reaches this point in time when he has some state in his brain, and he renders his thoughts into Arabic. But for the rest of us, this Arabic document's completely unreadable, right? So translation, essentially we humans have taken other humans that they've learned in another time and with the different style and mood and spelling, and having a completely different state, but we taught him 2 languages. And he's able to take the source language written in some source, Arabic for example, and render it into English. And what we'd like our system to do is to operate the same way. So we call this document A, document B, a parallel corpus. And our machines will try to produce alignments between these documents, as well as produce translations. But you can see that there are lots of processes inherent here. For example, co-reference and anaphras. The original author or the translator could use pronouns in one of the languages, or the author could have used a pronoun and he stick the real name in, and so on, and causes all kinds of problems when you do processing at the sentence level. And our systems to date have not gone beyond sentence level things, okay? Although we'd like to get to document level translations. So I'm always a proponent for collecting data exactly as the task that you're trying to do. And so you'll see that at least for word alignment we were successful. So far in translation we have not been successful. We have a little bit of data that's human edited, but it's not the same thing as translation.
What else do you consider part of that state? I mean, obviously anaphora are sort of a surface example.
Right.
What else do you find that in translation you can't do it unless, for example, you could guess the state of mind of the original author? Or
I mean, so if you think about the weblog domain or chat, it seems like when you render these acronyms and so on, there's a lot of thing that the system needs to now know before it can translate this. Right, and it's not clear to me that there's an easy way to get this.
So it's a state of knowledge in some sense. It's
right.
A state of, so you're not thinking in terms of the sort of political disposition of the author?
No, no. I mean, maybe we'd like to capture some of that, but...
Hamas is a terrorist organization or not depends on your state of mind.
Right, right.
So you're not going that deep, you're just saying...
No, not that deep. But, you know, a lot of times when you look at the error, you can see clearly this is the parallel corpus is doing this to us, okay? So I'll mention some of these things as I go into translation. Okay, so direct models, like I said, you know, this work is, there's a lot of history to this work. And it's in contrast to the source channel models in translation. So the prior art, Kishore in 1997 and 1998, almost 10 years ago, published these two things in the DARPA Communicator Days, translating between spoken requests and database queries. And those, you know, so he already used the direct translation phrases. And Franz Ock also, most of his work and most of the work on recent phrase decoders, they're all direct translation models, really. So for word alignment, there was this paper by Colin Cherry and Dekang Lin that it goes beyond HMM alignment, but they didn't have data. And we had two papers, both at HLT, talking about our alignment and translation work, which is what this talk is about. Okay, so alignment. So here's a picture of the alignment process. And at the top, I've shown an English sentence and an Arabic sentence. And by alignment, what we do is it's a left to right process. We're going to start with the first word, E0. And we're going to say that we hypothesize that it aligns to any one of these Arabic word positions. And let's say, for example, that it comes from A2. So one of the theories will be A2, and then we're going to extend that theory. And then we'll get to the E1 position, and then again we'll hypothesize that it goes to one of the A states. And let's say this time it comes from A1. So now we have a path. We aligned E0 to A2, and then we've gone to E1, which has been aligned to A1. So we have this path as part of the history. When we consider E2, we now also know the state positions that we're considering, also the path that has been traversed so far. Okay, so our problem is given these two sequences, this pointer sometimes works.
I'm going to go and get you a low text.
That's okay.
The first button.
The first button? Okay. Anyway, so what we're trying to do is maximize the alignment is a configuration. It's given by the script L. And we'll factor it into a bunch of decisions for each of the link decisions that we're going to make. So that distribution, you know, is a product of each of the LJs, and you're looking at all the LJs that you've done so far. We again factorize this model into being a language model on the transition decision so far, and then an observation model that given all of the A's and E sub J's to predict this L sub J. In particular, what will be really interesting is the A sub L sub J, the Arabic word at that position that you're linking to, and the E sub j, because that is our normal model 1 type alignment, right? But you can look at all the context around it. And the nice thing about maximum entropy is you can ask questions both on the histories of the distribution as well as on the futures. So this is a case where things are you can ask joint questions. So what was really neat about our approach is, for the first time we have data. We hired enough annotators, and we gave them sentences in Arabic and English, and asked them to mark the correspondences between the words. And back when this work was published, we had only 10,000 sentences, but from LDC and from other data consortia, we are now up to 37,000 aligned sentence pairs. This aligned sentence pairs goes from a tokenized unsegmented Arabic to tokenized English. This is sometimes a problem because once you've done human annotation, if you decide to change something, for example, the segmentation of the source, thank you, of the source, your training data is no longer valid. But that's a problem with the supervised approaches. But what we do is when we do change the segmentation or tokenization, we try to project the alignments into this new space so that our training data, we salvage as much of the training data as possible. Okay, so in terms of inter-annotator agreement, this was a few years back now, about 3 years back. We had this annotator MN and another annotator YA. You can see that the task is at least intra-annotator, it's in the mid to upper 90s. And inter-annotator, it's in the low 90s. Also that, when he does it, MN2 is, you can give him the task that that a machine has aligned the two sentences, and then he's just doing correction. And then in that case, he gets very good intra-annotator agreement. But if he starts from scratch and does the sentences without any alignment help, then he's not very good. He's 92.4 and kind of matches the inter-annotator. So it seems like for word alignment, at least, the low 90s is what's possible in terms of agreement rates.
Why do you call this beads?
Oh, sorry, those are beads is just another vocabulary for sentence pairs. Okay. Everybody creates their own jargon, so this is an IBM jargon. Okay, so like I said, in our model, we have this language model or transition model on the linked decisions and an observation thing. So we're going to talk about that transition distribution first. That transition thing is, once you've aligned an English word, then probably the next English word is going to align somewhere close to the original decision. That's the intuition behind it. And so what it does is, this first term is just a term 1 over distance, okay? And why it looks so complicated is, it has the notion of a frontier. As it's aligning, it's trying to remember the last Arabic state that was aligned to. And if you move somewhere else in the sentence, it can use either the current last position or the frontier position. So that's the max of L sub j. It's the rightmost source position. Okay? I'll give you an example of this so that it'll be clear. And then another term, which is just dependent on the number of items that we've already aligned to this state. Now, I always get a lot of resistance by doing this type of formulaic models. But we have tried putting these as features into our maxent model, and it doesn't work near as well as 1 over distance, okay? Because of sparsity and lots of other issues. So what we do now is we have distortion type features in our observation model, but we'll use this model also. Okay, and if you look at the original distributions, they're just the product of two things. So you can weight, you can have an alpha on the initial distribution. So it just weighs the two distributions.
That formula is a quick question. So what you're saying it's essentially 1 over distance because that's the LJ minus 1.
Right,
term.
right.
But for example, if you had left a hole in the Arabic sentence, not aligned it with anything, and then for some English word you consume that word, then the next English word, it could align to the word that's after the frontier.
Right.
You won't consider it a big jump. You just consider it advancing the frontier.
Exactly.
Okay.
Exactly.
And what's that cost, NJ?
NJ is a number of It's the difference in the E positions that have aligned to the state. So if you align E0 and E2, then that's a difference of 2, and you've aligned 2 items. So, it's a difference of 2, and it has 2 items. So that's more, it's more expensive to align things that are far away in the English sentence to the same state. Okay?
I wasn't getting the intuition.
Right. Okay, so here's a graph that kind of shows this. The red line is what's normally done in HMM type word alignment. It falls off as 1 over distance. And usually for the self, we're at the state 16. And so if, there's a self loop cost, and so that's maybe a little bit less than 1 over d. Okay, so I've missed a couple of points. The last state in our Arabic sentence is a special thing. It's a state that essentially describes when you, it's an English that is not aligned to any Arabic state. Okay, it's a null sept. Okay, so you might have a special cost for aligning to that state. But the shape of the function is essentially 1 over d. Now the green curve is the formula that I just described. It has lots of zeros because these states have already something aligned to them, but mostly it fits as 1 over d. Okay, and here there's something else that was aligned to this state. So there's a frontier notion. So aligning something close to the frontier is okay. Aligning it to the last source position is okay too. Okay? So that's the intuition here. Okay, so the observation model. So that's the second part. Here we decided to use maximum entropy to do this. The features are, it's the word position. It's not the Arabic at that word position, it's the word position. And you'll see why that makes a difference here in a second. So it's a complex feature. You can have, for example, lots of things about that Arabic word. So in this example, this is the Arabic word. This is a possible segmentation of that Arabic word, and it has some part of speech too. So here we're aligning the word document to this Arabic word, and really the future is this entire object.
You're talking about the features.
The features are questions that you can ask about document and any of these things. This is the future here.
This is a future.
Right. You're aligning English to the Arabic, so the state becomes the future in this model. Okay? Okay, so here's some of the features inside the model. The way to read this is, here's the English things, C and BC. In Arabic, you see the C part of it. It's part of some abbreviation, and NTV and so on. There are alphas. It's the normal accent. That's a product of the alphas, right? It's an exponential model where you multiply the alphas. You can see that aligning the to period is very bad. And also that the model uses this feature a lot, that aligning an unknown word to an unknown word is pretty good. And it occurs 3,900 times in our 10,000 sentence alignment corpus. Okay, alpha is greater than 1 usually is a model voting, and it's saying that it's a good thing to do. Alpha is less than 1, it doesn't like to do. Okay, so here.
What is F sub 0?
F sub 0 is the null state.
Oh.
So if you align, it seems like 4 times in our corpus, the English word help is aligned to null. It's unfortunate, it's usually probably not good to do this, but we do allow the null subfeatures in our model.
Would you like to have null states interspersed between the words of the Arabic states?
What you're asking is a context-sensitive null. And yes, but in this model it wasn't done. Okay, so other features look at the English words and then the segmentation of the Arabic. Similarly, the alphas. So here, one interesting feature is comma goes to the Arabic wa, which means and. So comma and are good translations of wa. Another feature is in the English, we have WordNet information. So you can look up the WordNet synset ID and class all the words that belong in a synset together. And so here, this synset is aligning to this Arabic source. that Arabic source seems to mean injured, so you can look at the alphas and see that the WordNet alphas tend to be higher because they're classings of English than the lexical features. Here's another feature that is used in word alignment, and this is the string overlap. Yeah?
What kind of regularization do you use for alphas?
It's a Gaussian prior.
So they can go negative?
No. The alphas are always positive. The lambdas can go negative.
E to the lambda. The
Yeah.
lambdas are Gauss.
The lambdas are the, right. Right, so this is a spelling overlap feature. Lots of names in Arabic, if you Romanize the name and you look at the English, they have a lot of similarity. And so this is a feature that measures the string kernel distance between the Romanized Arabic and the English. And so if you have, if you have no match between the two strings, then there's still a chance for linking the two of them together. And what this usually means is that these are words, these are not really names. There's just some prior probability of linking them together. If there's some match, then the alpha is much better. It occurs about the same time as no match. Good match also is about the same, but the alpha is much better, right? So these are really names, and exact is most certainly names. Names and numbers. You'll notice that this feature helps you to tie all the numbers together.
For numbers, it should be pretty easy.
It is, but if you think about the problem, when you do number classing, so if a sentence has many numbers that have been classed, so you have many $nums, and now you have to choose which one the English one belongs to. And this feature helps greatly, because you just look at the overlap. Okay, and then some dynamic features. These are features that say, the previous target "and" was aligning to this word when the current target is witness is aligning to here. Okay, so it's a compound feature. This feature fires on the hypothesis, right? As you're searching your word alignment space, you have to extend these theories, and then these features will fire on that lattice of possible decisions. You can see, for example, agency France press. So this seems to be agency, and then France will align to France. And when France aligns to France, press seems to align to this word. By linking these together, it learns longer context. So here's the performance of this algorithm. In the paper, I cited contrast between Giza and HMM and Maxent. And it seems to be like 70, mid-70s for HMM and maybe upper 70s for Giza. And we were at 87 a few years ago. These are the different feature types I just described, and the number of them in our corpus. And these are just feature ablation studies that show, with different combination of the features, what type of performance you get. Essentially, the only thing to remember is that, segmentation seems to help a lot. Okay, so wait, this jump here is the generic feature, which is the spelling overlap. So that's about 4 F measure points. And then the other jump is between the segmentation. The Arabic segmentation seems to help a lot. But these are, language-specific and task-specific type of features. You have to understand the errors and then engineer the features to match, the problem. If you take a look at the source length versus the alignment F measure, I don't see any real correlation between F measure and sentence length. So we're good on shorter sentences and about the same on longer sentences. So no real correlation. Other things to note about this model, the Gaussian prior has very little effect. We tried to do a line search for that, the variance parameter. It doesn't seem to do much. Without the Maxent model, if you took a look, if you go back to the original equation, you can just remove the Maxent portion and say it's just a transition cost plus a model 1 cost. You get an F measure of 74, which is about a little worse than HMM. Some of the new features since we did the paper, we have a Model 1 proxy feature. What this feature says is, I'm an English word like the, and my head, according to my parse tree, is aligned to this Arabic word, then what's the probability of linking my determiner to the same thing? And that seems to have improved it even another F measure point or so. And then some features based on parse nodes. If we look at the breakdown of the aligner against corpus size, you'll see that, varying it from 1,000 sentences to 10,000 sentences, the content F measure, which is, significant words, it doesn't really change much. So you really need only like 1,000 alignments for the content. But the function words, the determiners of and the and so on, as you get more and more data, the content, the function word performance goes up. I have not plotted it for 37,000, so I don't know. Okay, so that was the piece about word alignment. And I'd like to transition to, unless you guys have any questions about word alignment. Okay, so the next part of the talk is about translation. And what we noticed was, even though we had this aligner, we used it in a phrase decoder, and it didn't improve performance of the phrase decoder, marginally, like a half a point to 1 blue point. And we were quite disappointed with this, and we tried to find out why having better alignments did not improve translation. And so let me just give you an example right away. You notice that, lots of times in Arabic, you'll get alignment patterns that look like this. There's a contiguous sequence in English that is broken. There's a variable. And so you cannot extract a block of the central committee when you have an alignment like this. And the better the alignment F measure got, the more and more richer of these type of structures there are. So phrase decoders that want to get contiguous long n-gram sequences were just failing to extract blocks when the alignment F measure goes up. And so what we wanted to do was come up with a translation model that was able to use these type of rich structures and be able to decode with that. Okay? So essentially we have variables on the target side. I haven't shown any, but there could be potentially variables on the source side also. For example, the French n'est pas going to not in English, right? And here's another one where, you'll see that some of the time you need longer phrases to produce the English target, but you don't need them all the time, right? So the phrase decoder tried to memorize all the source n-grams, of arbitrary length here and target, just satisfying the alignment constraint. But in our approach, what we did was we took the simplest set of blocks that could do this type of translation, and so then we end up with a much smaller set of translation blocks. And the power, we moved the power from the translation blocks into features of the model, right? So the classifier, so what we're going to do is treat translation as a tagging kind of problem, okay? So whenever we're given some source sentence, and normally if you think about name tagging or something like that, we would like to know for every source position whether it's a name or some other thing, okay? So here, instead of being a name or something, we're going to produce the English translation for it. And the English translation is going to become our class. A rather large class, maybe not quantifiable, but still there are vocabularies and there are ways around it.
What do you mean by flip of a coin?
Right. What did I say? Right, something, we need to know what the history of the model is, right? And when I was giving this talk before, it's just essentially what we want to do is, predict what would happen when we flip the coin, right? It has two heads, right? For translation, what we do is we will run the aligner, an HMM aligner, a Maxent aligner, whatever alignments we get, and we'll go to every source position and pick up the phrase that we want to produce, and that'll become its tag, right? Okay, so the history of our model is the source words, And this is a very good choice, we think, because by definition, the number of source words in our corpus is well known. Whereas for a phrase decoder, when you have arbitrary number of n-grams for every sentence, it's hard to know what the chunking is. There's an extra level of information that's needed. What's the best chunking of this sentence? That's the overlapping histories. Okay, so we share the generation story with the phrase decoders. So how this works is we're given a source sequence, and then we choose a source position within the source sequence. We'll choose a translation string for this source position, and then we'll mark the source position as being covered, and then we iterate until the entire source sequence is covered. This is our normal translation process, right? We haven't changed it that much. We'll still choose a source position, but we need to know what the jump is from the previous source position, right? We'll choose a translation string, but here we need to know whether we are producing a word or a phrase, right? Whereas normal phrase decoders, they're impervious to this. Then we mark the source position as being covered, but if you're generating a phrase with a variable, then you can't mark it being covered until you've generated all of it. You have to mark it partially covered, and then when you generate the entire thing, then you can mark it completely covered. And then we iterate. Okay, so our model looks something like this. It's probability of, we're choosing some target given the source sequence. Normally we would sum over all possible alignments of between the target and the source. But we don't have a lot of alignments. We're going to stick with the one best Viterbi alignment that we're given between the source and target. We'll break it down into a bunch of decisions. We'll say from this source we'll predict how many target things to produce. And then we have this distribution. It's exactly identical to this. Okay? Except I've pulled out the history, the previous targets that we've produced, the previous alignments and jumps, and the entire set of sources. Of course, that's intractable. We can't look at the entire source sentence every time we want to do this prediction. So we'll restrict ourselves to the window of source positions around the current generation that we're doing. Also, we'll restrict our target to be just the last couple of positions in the target. Typically, we run with 5 grams. So this is not I minus 1 and I minus 2, but it's the entire history according to the language model. Okay? Now, from here to here, the only difference is that, instead of looking at the absolute position, we're going to look at the relative difference between the current one and the previous one. And from here to here, I haven't done anything except replace this by an index called j. Okay? So our final model says, given the source around our current generation point, the previous targets that we've produced, predict the jump and what we're going to produce at this point.
You make the assumption that the jump is independent of the actual position, because you remove
yes.
A, which is pretty reasonable, of course.
Right.
Because you remove the A from the condition.
Right, I did.
So when you look at S A minus I to A plus I, do you consider the fact that some of them may already be covered in the sense that you just defined covered?
Yes, you can ask a question. Is my previous S sub A, is my previous S AI minus 1 covered or not?
So in that sense, you have more info. You have not lost track, for example, of the previous alignments.
No.
Because it might be covered by something much further in your history.
Yes.
So you haven't really dropped that conditioning on A0 through AI minus 1 completely.
No, not
to
really.
the extent that it is.
You can ask a question about the coverage state of this position, so you can get the whole history. Okay, so we take that final form here and separate it into 2 things. This is the step that I was saying. You can still have, it's a product on T sub I. So we're going to pull out a form that looks like the language model from before. And then the remainder is our translation model. Okay, is that clear? Okay, so in the work that I'm going to talk about the rest of the time is this translation model is always generating, T sub I is a phrase. It's not a word, okay? And I think it's still possible to do a word, but we do them as phrases right now. And the reason for this is, the language model is already doing things on a word-by-word basis. So it's tending to make things shorter. And this model, by considering T sub I as a phrase, it's impervious to this, or it prefers to actually do things longer, if you think about it. And so the competition between these two models, I think, is a good thing. But I think it's entirely possible that you could do it on the word basis and still be okay, and probably more correct. Okay. So now I've described to you kind of the process and so on. So we said, okay, maybe, phrase decoders just have n-gram type blocks. Maybe we could define some terminology for our types of blocks. And so what we have are the following set of block types. We have deletion blocks. This is essentially a source position that produces nothing. Okay? And for Arabic, it seems to be a small set of words that can produce nothing. For Chinese, it seems to be a lot more things that can produce nothing. Chinese, the language has like measure words and few other connectives that don't have a correspondence in English, right? So there seems to be quite a bit more of those, but in Arabic, far less. A small digression, I really believe a small amount of training data would allow us to get this list exactly without having to create it on the fly or have human knowledge. But right now, these lists are being made by hand. Our normal blocks are source size 1, producing m target words. Phrase blocks do n source positions, producing 1 or more target. If it produces more than 1, then we say it's a non-compositional block. These are idiomatic phrases like Humpty Dumpty or peace be unto you, or things like this, that there's maybe not a one-to-one correspondence between the words.
The M and N can be
as large as you need to, right?
in your system.
I'll have some histograms of the sizes, but there's no real restriction. I think 12 or something like that. And then there are spontaneous blocks. There's nothing on the source side, but we need to produce some target. So this is like the determiners, the, in the, and so on. Okay? Okay, so variables. I've already kind of hinted at them before. So here, the source word LL, J, and P. I don't speak Arabic, so what I do is I Romanize it and spell it out. LL, J, and P produces of the committee, where X is a variable. And I said the French example before. But to contrast to the work of Hyro, we absolutely require these anchors. We don't do variables at the end of phrases. And we're only going to take the minimum number of phrases and variables as required. We're not going to be very general. Essentially, this is the algorithm. If a 1 to m block cannot be extracted at this source instant, then we try all types of other relaxations to get a longer non-compositional block, perhaps. So we end up with this type of a histogram. This histogram, what it shows is this is for a phrase decoder, and this is a general system. And this is a test set specific or a subsampled kind of system. And you can see the shape of the matrix. So this is the target size. This is the source size, and that's the target size. You can see lots of blocks are 1, 1, and the shape of the matrix. And you can see, if it's test set specific, the counts all go down, but essentially the matrix form stays about the same. Okay? And this is the DTM system. It essentially has very small number of blocks. It's not able to extract anything that's longer than 5 target words. It's not a cap that's placed on it. It's just, the data.
We would expect this block of numbers, the big numbers, to move slowly in a diagonal, but they don't.
There is some kind of diagonal.
There is some, but it doesn't go up to 12 or that.
No. No. Okay, so to hopefully make things very clear, I've given you this example. This is this small Arabic sentence, and we're currently here, and we've just translated this, okay? So we go to our phrase table, and most of the thing that the direct translation model has is the engineering of these, the blocks to have variables, and to carry along with you all of the information to ask questions at the right moment, right? So for this source position, we can produce all of these English phrases, okay? And for this source position, these phrases, and so on. And so the training essentially happens, at this point, these can be produced, and of them, one of them is true, right? We don't need to know the truth, but we're, in max entropy, we're just counting up the feature expectations and adjusting the alpha for this future, right? So here I've shown you, this is the true future, and the rest of it is the denominator, okay? So the jumps are marked, right? So from this, I think, it should be able to be implemented. Now there's one note, there's the prior, and the prior in the distribution is just a phrase count, okay? Essentially the unigram occurrence of this phrase block in our corpus. Okay, so review. A block or a phrase pair is just a pair of sequences S and T, which is context-independent translation pair. The features are support for this distribution. And the key difference between phrase decoders and the DTM decoder is, you have very simple blocks, but the features are complex. And I'm going to describe the features next. Okay, so the features are all binary questions. They're heavily lexicalized. They'll ask questions about the segmentation, the lexical context of this production, the part of speech, the coverage, and so on, okay? And the so on, I have a couple of things that I can tell you what I'm working on now. Okay, so like I said, in our phrase table, we have all of this information. We have the source word, the source segmentation, the source part of speech, and anything else that you could decorate about the source. On the target side, we have the target words, the part of speech. At this point, that's all we have, okay? These target part of speeches are collected from the corpus. They're not being tagged as we're doing the machine translation. But in our parallel corpus, we've tagged the English side. And when we extract a phrase, we also extract the part of speech for that phrase. Then when we hook the phrases together, we can ask the question, are you putting an in next to a DT or whatever? Okay, so here's some of the features. So it's this is the current production. So you can ask the question, is LLJNP producing of? Is LLJNP producing the? And that's the list right there. You can also ask the segmentation question. This LLJNP has that segmentation. So is L sharp producing of? Or is LJN producing committee, for example? Okay, these are all good things, right? They're much better than the Model 1 cost for LLJNP producing this phrase.
Of course, you have millions of these.
Right, right. I think I have a breakdown at the end of the number in each feature category. So you can ask lexical questions about the context. LLJNP is producing of when the left target word is Politburo in this sentence, right? And a lot of them, right? But typical phrase decoders, when they do translation, they're using a long block, that's true, but they capture all of that context within the block. But here, when LLJNP is producing this target phrase, it can have lots of features that ask questions about the context, and they all add into this production. Weigh in on this production again. Okay, so some part of speech features. So here, this NN is producing in on the target side, and NN is producing DT, and so on. Okay? Coverage type features. So LLJNP is producing committee when the right word has been covered, yes or no, right, and so on. I mean, the reason for all these features is, you're going to do a lot of search. Remember the model? It's T sub j given T and j. That you're producing this block with all possible jumps. And you're trying like skip 4, which essentially means you're going to try all possible permutations of this 4. So you really need these features to help. Otherwise the model gets lost, right? It can hypothesize crazy things and the language model likes it, and you wouldn't, it would be very bad. Okay.
I have a question. Can you go back to the previous slide?
Yeah.
So if you have a feature of the kind, let's say that you're trying to actually translate the sentence at runtime.
Yes.
You'd be going through producing the Politburo of the. And the thing is that this of the comes from this feature which aligns, I don't know what that word is. I think it's ILJP.
LLJNP?
Yeah. So maybe it's supposed to produce of the central committee, but producing that, of course, requires inserting the word central.
Right.
And you haven't done that yet. So I'm trying to figure out how the decoding will work. Will you produce something with a whole, and if you produce something with a whole, how many words go into that whole?
Right. These are all parameters of the search. So what happens is you will
do some look ahead in your search.
No. What happens is, the Politburo gets produced.
Yeah.
Then LLJNP will produce of the, and that hypothesis will get marked partial. And then when a theory is marked partial, you're allowed to explore other theories that mark the other positions as being covered. Finally, you'll have to come back and you'll see this theory is already in partial state. I have to finish it. And so when you finish it, you'll produce committee and then close it. Right? So it's just one additional. So there's usually a coverage vector for phrase decoders.
For example, this right coverage, I don't know whether it's right coverage, but yeah, wherever before you put in committee, you decide that central has already been produced, or that the Arabic word which is in position 4, that has been covered.
Yes.
You will get that feature only when you produce committee.
Committee, right.
So
the two productions are different. Of the is different than committee. There's actually two things that the LLJNP is producing.
So then you have to watch out that of the doesn't get pruned early, because if it did, you'd never get to the point where you.
Right, right. Actually, LLJNP has a T sub I that has a different J for of the and committee. Committee has J minus 1 because you're jumping backwards. Of the has J plus 1. Right.
Because it's one from the previous, from Politburo.
Right. Training is not difficult for this because the number of events is still it's quantifiable.
Right. No, training is
Right.
okay. I was thinking more about the decoding.
Okay, so here's one last feature type, and these are based on classed words. Yes, we have millions of sentence pairs to do Arabic-English translation, but you still don't see all words jumping all possible transition things. So this is one way to alleviate for those really rare source words. So what we do is all count one things according to our vocabulary is classed into star, 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 and then we'll say, it's a rare thing jumping by distance 1, and the system seems to like it because its alpha is greater than 1. If you jump by 2, it's pretty close to 1. It's probably okay. Everything else, it's saying it's not very good, which matches our intuition. And it also smoothens the distortion model that's being used in the system. Okay, so some experiments. So I'm going to report on the Arabic-English Gale Devo 7 data. It's something that's recent. The paper actually talks about MTO6 and MTO5 and so on, so you can refer to that. What we do is from our parallel corpus of 7 million sentences, we're going to produce a subsample, and by this we mean just sentences that look close like our test sentences. Okay, and for every n-gram, we'd like to have 20 examples of this n-gram if possible. And so doing.
In the test data.
Yeah.
You want 20 instances of it in some 20 different sentences.
Right, right. Okay, and what this will do is reduces it from 7 million sentence pairs to 300,000 sentence pairs. This seems to be important because we want to be able to compute this model and to translate today. And that's the primary reason we do it. The other reason is it seems to be a kind of adaptation to the test set, and it seems to give performance like 1 to 2 blue points over a general system. And we have a set of alignments. Like I said, we have both HMM alignments and maxent alignments.
How many of the test engrams are you able to find 20 counts?
I mean, the OV rate is in the 1% to 3%, that range.
So that's OV, so you can't find nothing.
You can't find
But
anything.
you have a count threshold of 20.
Ah, yes, okay.
What fraction gets to 20?
I think there is on the order of like 10% of source words that don't reach the 20. Okay, so here's a histogram of the type of features for each type of alignment and the number that are selected in the final model. So for this particular test set, we have about 6 million features, and you can see, there's maybe 20 different types of questions. The one that's marked 1 is just the source word and the target word. So this would be like a Model 1 type of a feature. Okay, so do any of these features make any difference? So this analysis kind of shows you that. So if you use all the feature types, you get this result, minus 7.15. Okay, so I should say what this measure is. There's two metrics. There's blue and there's TER. And what we use is a combined metric called TER minus blue. And so that's why it's negative. Okay, the best you can do is minus 50. Minus 30 is thought to be about human performance. The reason we have two numbers is we measure both an average TER minus blue, also on the bottom of the set of, these are the set of bad documents, or with the tail of the distribution, what the performance on the tail is, and that's the second number here. And so what I'm going to show you is that as I subtract the different feature types, what happens to performance. So if you take away the part of speech, it seems like the tail gets worse. Lower is better in this metric. But the average gets slightly better. Okay? Maybe not significant. If you remove the source part of speech and the target part of speech, it gets a little worse. The average gets a little better. And so on. Okay? But you can see we're staying in the 7s. Okay? We haven't done much to the performance. And really, if you take away all the features, it seems like the tail is much better than when we started out. Okay? And the reason we think is because, part of speech taggers and the other types of information we're using, probably on the very poor documents, these are breaking down and not as good. So we don't know about these other type of features that we're using. But the tail is...
Overall or on a particular genre?
This is Gale Devo 7.
So it's the whole Devo 7?
It's a whole Devo 7.
All the BN, BC, everything?
Right, right. This is Newswire, sorry.
Oh, Newswire, okay.
There's only Newswire.
Oh,
right.
just Newswire.
Right.
Okay. That's what I meant.
Okay, but doing all of that, we haven't really impacted performance. So where is the real performance improvement from over phrase decoders? And you can see that here in the bottom. If we take away the source left target bigram, by this I mean what the previous source word was when we produced this target, then you lose a half a point. And you lose almost 1 point on the tail. If you take away the right context source, then you lose again another point almost, or 0.7. Right? And again, you lose 0.4 on the tail. If you take away the source left, target left bigram and the source left, these are trigrams on the target side, you lose another point. And this seems to be about the performance of most phrase-based decoders. So the features do seem to help. Okay, so I think I've spoken to you about word alignment and translation. And I think, more than anything else, my contribution has been as a framework. You can easily try features inside this model and train it, whereas features, the traditional way of doing maximum blue training for phrase-type decoders is not always guaranteed that it'll work. And there's no guarantee here either that your feature will work if you design a bad feature, but at least, I don't know, I feel somehow more comfortable with maximum likelihood and maximum entropy training than maximum blue training. We can go from a test set to a translation in about 7 to 8 hours. this framework has some disadvantages, and that's, formulaic things. If you want to translate manuals or other things where, repeated long phrases are being translated many times, and you're better off perhaps just memorizing the entire long phrase. And we don't do that here. The other disadvantage is that, we have to run skip 4 because most of our blocks are very simple blocks. We have to try a lot of reordering sometimes to get the English sentence. And this is typically much higher than what phrase decoders run. They run 0, monotone, 1, or 2. And so we're doing a lot of search compared to phrase type decoders. What we have going on in the lab right now is more explicit distortion models. Essentially, even though we're searching skip 4, maybe we can associate a cost with when we skip 4 words a little bit better than what DTM does. And the other thing is there's quite a bit of work on source-side parsing and then deriving features on the source-side parses to help, for example, to know that a subject has been covered completely before we translate the verb and so on. Okay? Sure.
I had a question. If you could go all the way back to the graphic you had about the word alignment, when you were showing the impact on content word versus. Yeah, this one. This is intriguing that with 1,000 sentence pairs or so, you pretty much learn your content word alignment. And then the rest of it is just helping you with the overall, because it's actually helping you fix up the
function words.
Is it, does this play with the fact that you take all these singletons and convert them to stars, or that's not involved?
No, it is very important. Remember, this model is trained on 10,000 sentence pairs.
Okay.
So when you apply it in real life, there's a lot of OOVs. The OOV rate is like 20%.
Okay.
And so the model for the unknown word is very, very important. And so spelling overlap and the distortion, even though you haven't seen this word pair, the fact that it just occurred right after something that you do know and that you can align it is very important.
So this is not going to translate into, not in the literal, not in the task sense. From this, I can't conclude that content words will be well translated in the translation system, because in the training data they were well aligned.
No.
Yeah, that was my assumption too. Yeah.
So in other words, the reason they worked out well is because when you do see the correct translation,
Yes.
you know what to align that content
Yes.
word to.
Right.
But if you had to hallucinate or hypothesize that translation, you wouldn't know what to do with this content.
Right. Right. Usually what happens is on these very rare things, actually not very rare, but count 5, count 10 kind of things, there are a lot of different English will align to the source word. And now this source word has a very great amount, very perplexing things to translate into, and you don't know how to pick between them.
No, I was just wondering whether, well, I guess you can still use it in your in the alignments, because Damianos, of course, has a similar problem aligning multiple system outputs to each other.
Mm-hmm.
And then it's an all English problem, but there I was wondering whether this would be useful. You should probably look into the alignment in the source, and if 2 words.
Right.
Yeah.
If 2 words are being produced by the same source, then it's likely to.
That if one source word has a good spelling distance to the target word and the other one doesn't, you can assume that the other one is the one that's wrong.
Right.
Because right now,
It was
Right.
not used in this discussion when she was speaking words.
so it's intriguing that just that trick with substituting them with stars basically gets you most of the way, or rather looking at the string similarities.
Right. I mean, in Arabic, most names have some common word translation, right? And so that's I don't remember the examples, but most names have some some common word. So if you knew the string similarity, then you'd get it. Otherwise, it's hard.
I guess it helps that Arabic is sort of has a phonetic script, if you will.
Yes, that we can Romanize it and render it close to English. Yes.
And you say that it takes almost 6 or 7 hours to decode the test set, and most of the time is spent talking. What?
It's probably 5 hours on the maximum entropy training and 2 hours on the decoding. We do typically 4 to 5 iterations. And it doesn't seem to, we've run it out for 50 and 100 iterations. It doesn't seem to change much.
One other question, it's maybe a stupid question because I wasn't paying attention. Does your maximum entropy training require you to do word alignment first? Because some of your features ask questions about
Yes.
this and that.
Right.
So it's not like it is all built in and the same training does
No.
the alignment and
No. The translation setup, I keep dropping this. The translation setup is you're given a corpus of sentence pairs and the alignments.
so yeah, it wasn't.
You can't.
So in that case, do you do the alignment also after you do the subset selection based on the test set?
No, we
You
normally
like that
we do the alignment up front on the entire corpus.
Okay, got it. Because I think that's in our pipeline, that's one of the things that we've been struggling with. Because
It's slow.
the alignment takes a lot of time.
Yes.
There's a whole visa run, and we tend to do it after the subset is selected.
Right.
And so right now, who's working? Are you working on it or Jonathan?
I'm doing it. We're in the process of switching it to.
Alright. So we are sort of
We found that if we align it up front and we just extract all the alignments, it's very fast.
right.
So
Okay.
And you have results with the two kinds of alignments? The
HMM and I do, but I don't have a slide on it.
I mean, you told me that it doesn't.
I'll tell you, the HMM alignment is probably half a point worse than the Maxent alignments, but not worse, not much more than that. But on the tail, HMM is slightly better.
Thanks.
That's a dirty secret.
Thanks.
The problem with the tail is that you cannot really compute.
Yeah, I don't know how to, its variance is very high. So 1 point difference, right. But it's all the work on Maxent alignments and supervised alignments and so on, you really have to question, whether it's really useful still. So for new languages, we just do HMM alignment. Okay?
All right, well, thanks again.
Sure, thank you.